pajamas. I'm happy saying pajamas. I'm going to say it as often as I can. Now we have Kelly Isham from University of California, Irvine. She's going to tell us about low bounds, the number of subrings, and z to the n. Take it away, Kelly.
Hi, Fatma. Thank you for the introduction. So yes, I'll be talking about lower bounds for subrings and z to the n. So to start, let's just define how we'll think about subrings for this talk. So a sublattice L in z to the n is multiplicative. If we take two elements in the lattice, multiply component-wise, and that corresponding element is back in the lattice. And so we'll say a subring in z to the n is a multiplicative sublattice that contains the identity. So what we'll be studying today is this function fn of k, which counts the number of subrings of index k in z to the n. Since this function is multiplicative, really it just suffices to understand the number of index p to the e subrings, so prime power index subrings. And there's many ways that we can study this. The way we'll do it for this talk is we'll think about these as being the coefficients of a particular zeta function. So the subring zeta function is going to be defined as follows. So it's a sum over all the finite index subrings in z to the n, the index to the minus s. And so if we just collect all of the terms that are the same in the sum, we get exactly these coefficients, the number of subrings of index k times k to the minus s. This zeta function has an Euler product, and so the local factors are just now these sums over the coefficients where k is a prime power. So this again kind of illustrates why it really suffices to study fn of p to the e. So our first main question is, what can we say about the divergence of the subring zeta function? Kind of the ultimate goal would be to give the abscissa of convergence, but that seems out of reach so far, so at least can we give some sort of information about where this diverges? And what that's going to tell us is something about this asymptotic growth of subrings in z to the n. So looking at the function that counts subrings up to some index and then letting that index go to infinity. So to start, we can give some results by Kaplan, Marcinek, and Takli-Bighosh. So there's a few ways to study the divergence. What they do is they define this simpler Euler product. So this is just the first two terms in the local factors of the subring zeta function. And since this is a simpler product, they can actually compute the rightmost pole, and they know exactly what the order of this pole is. And since the subring zeta function has to be strictly greater than whatever this value is for all values of s, we know that the subring zeta function diverges when the real part of s is less than or equal to 1. So this is kind of an initial result, and we're getting that this bound is a constant. The constant is 1. So they do this really to prove the following theorem about asymptotic, so the growth of subrings. So let's define formally what that is. So the function n of b is going to be the sum of the number of index k subrings in z to the n up to index b. So just counting all subrings of index at most b, and we study this as b goes to infinity. And so their theorem is they give an asymptotic function for this formula when n is less than or equal to 5. And so what they get is essentially b to the first power, so coming from this rightmost pole at s equals 1, and then they get a log term as well. The case n equals 3 is due to Daskovsky and Wright. the case n equals 4 is due to Nakagawa. And so in these cases, 3 and 4, what these authors do is actually describe the Subring zeta function as a rational function in terms of the Riemann zeta function. And so using that, they can explicitly determine what this asymptotic is. It's a very interesting result that even when n equals 5, they're able to prove this asymptotic without knowing some sort of simpler expression for the Subring zeta function. When n is greater than 5, they can still give lower and upper bounds for this asymptotic growth. For this talk, we're studying lower bounds, so we can focus on the left-hand side. And again, it's a b to the first and then times a log term. So another way that we can study the divergence is we can look at making one term in the Subring zeta function simpler, and then we can use that to determine divergence of the entire zeta function. So we'll use a proposition by Brackenhoff from his 2009 PhD thesis, which tells us that the number of index p to the n-1 plus d subrings in z to the n is bounded by this monomial in P. One interesting thing to note here is this bound only holds for certain values of E, so only when E is between n-1 and 2 times n-1. So later in this talk, I'll prove a bound that actually works for a larger class of E, but for now, this is what we have. And so just using kind of an analysis argument, let A of n be kind of this crazy function that I'll describe a little bit later. So using Brackenhoff's bound plus a little bit, so I'll attribute this mostly to Brackenhoff, plus a little bit from me, we get that the Subring zeta function diverges when the real part of S is less than or equal to this function in N. And then that just gives us that the asymptotic growth of Subrings is bounded by B to this function in N. So it might be hard to look at that. This is a maximum over integers D of this function here. So, well, what does this tell us? Well, when n is greater than or equal to 8, this result improves upon that of Kaplan, Marcinek, and Takla-Bighosh. And this function, if we could maximize over all real numbers d rather than all integers, we get exactly 3 minus 2 square root of 2 times n minus 1, so roughly 0.17 n. And then plus something that's no bigger than 1 over n minus 1. This is something I can compute explicitly, but just to tell you, this is kind of like a small part, especially as n is large. Really, the main contribution to A of n is this first term. So we see this is a function in n. This is going to grow and give us better and better results as n gets larger. So that's what we can say about the divergence of the zeta function as a whole. So we saw that this way we looked at bounds for fn of p to the e and then used that. So maybe what we can do now is study actually the divergence of the local factors. So knowing more about the local factors tells us just more information about the zeta function in general, rather than just looking at the divergence coming from one term in the zeta function. So the main input here, as I was hinting at, is we're going to find lower bounds for fn of p to the e. And the idea here is we can bound the local factors by this simpler series where we just take, say, a monomial term where the exponent is a function of n and e, And then we study the divergence of this simpler series. So the way we'll bound Fn of p to the e is not by trying to count subrings, but we'll try to count these things called subring matrices. So I just want to give you a little bit of a flavor of how this goes through. So Lou showed that the number of subrings of index k and z to the n is exactly the same as the number of n by n subring matrices with determinant k. So what is a subring matrix? It's a matrix in Hermite normal form that has determinant k. The identity element of this lattice has to be in the column span of the matrix. And all of these products, so these pairwise products, component-wise products of elements, have to be in the Z column span of the matrix as well. So here's kind of a really small example. When n equals 2, it turns out that the second column of this matrix actually just has to be the identity. So if you write out kind of what these closure conditions tells us this is the column 1, 1. Hermite normal form, one of the pieces of that is the matrix has to be upper triangular. So that forces a 0 here. In order to get determinant k, we have no choice. We have to put a k in the first spot. So what this tells us is there's exactly one 2 by 2 subring matrix with determinant k. So there's exactly one subring of index k in z squared for all positive integers k. It's a bit too hard to count these subring matrices, so we're only going to count a subset of them, which are called irreducible subring matrices. So what those conditions are going to force is that the diagonal is made up of just powers of p. The last column has to be a bunch of 1, so just this identity element. And then every other entry in this matrix has to be divisible by p. So the way we can write that is just pull out a p in all of these coordinates and then look at these variables here. And so now, counting the number of matrices that look like this, we need all these closure conditions still to be true. So if we set those up, we're just going to get a bunch of equations that need to be satisfied, and we just count how many of those there are. It turns out that if you make a bunch of these terms equal to 0 in special ways, the closure conditions actually just go away. So then you can count how many entries do we have to make non-zero. And so just doing kind of the combinatorics there, yeah, we bound Fn of p to the e by bounding the number of these subring matrices, setting a bunch of them equal to 0, a bunch of the entries, and we end up with this bound here. So this works for e greater than or equal to n minus 1. And if you remember what a of n looks like, it was this d times n minus 1 minus d part divided by n minus 1 plus d. So this looks a lot like e times the function we had before. But since we're optimizing everything over the integers, it's not as good as that. But still, it's relatively close to kind of what we had before. And so now using this, plugging this into kind of this simpler series I was talking about before, gives us the following result. So if we maximize this function over all integers between 0 and n minus 1, the local factors diverge when the real part of s is less than or equal to this function. Again, this is just kind of a difficult function to look at. What is this really? It's roughly, if we could maximize over r, 3 minus 2 squared of 2 times n minus 1, so roughly 0.17 times n minus 1. So we get a very similar divergence to the entire Subring zeta function minus that O of 1 over n part. So now we have more information about not only the divergence of the zeta function, but also the local factors. And so for the final couple minutes, I want to relate kind of what these results that I just shared tell you about orders in a number field. So let K be a number field of degree n, okay, its ring of integers. We'll define an order to be a finite index subring of OK that contains the multiplicative identity. And we'll define this function nk of b. We're going to count the number of orders, and we're going to order by discriminant. So it's the number of orders of discriminant at most b in OK. And again, we want to study how does this function grow as b goes to infinity. So the initial result in the same paper by Kaplan, Marcinek, and Takla-Bighoff gives an asymptotic when n is less than or equal to 5, and then upper and lower bounds when n is greater than 5. And so before, for the growth of subrings, we had a b to the first term. Now for the growth of orders, it's b to the 1/2, and then times a log term, where R2 is just a constant depending on the Galois group of the normal closure of K over Q. So if you want more information about that, I recommend looking at their paper. And then when n is greater than 5, they have these upper and lower bounds again. So they get the lower bound b to the 1/2 and then times a log term. So if we look back at that Brackenhoff theorem from before, and then we apply some sort of transformation from subrings to orders in a number field, we get that the asymptotic growth of orders ordered by discriminant is bounded from below by b to this function here, which is just 1/2 of what we had before. So if that's too difficult to look at, roughly b is 0.086, so 0.17 over 2 times n minus 1. And then we get a little bit more that's no worse than 1 over n minus 1. So the results from Subring tell us a lot about results about orders in number fields as well. So I'll stop there and thank you very much.
Perfect timing. Thank you, Kelly. That's all. Thank Kelly for a nice talk. And maybe we can have 1 or 2 quick questions. I had one. You call this a zeta function, and you said that the sum has a product formula. Is there more? Is there a function equation, or does it stop there?
So the only functional equations that are known are for n equals 3 and 4.
And is there a geometric origin? Is there something?
Oh, is there a geometric origin? Not that I know of. I think these are not studied too well. There might be more known in this specific case, but I'm not sure.
Awesome, thanks. We should look at chat. The questions in chat. Anyone else? I see raised hands. Okay, maybe not. Sorry, then I'll ask a second question.
Sure.
Do you prove low bounds for how many of these subrings, sublattices? Do you also have upper bounds, or is that much harder?
I think that's a harder question, especially for counting these sublattices. You could give some kind of trivial bounds by just saying maybe all possible values of the variables are possible. Some kind of better upper bounds come from studying the volume of these lattices and bounding that way. So that's how the Kaplan, Marcinek, Taklid, Big Hosh paper does it. But I would be interested in seeing if there's something we can say more about using this this approach to find upper bounds.
Oh, Guillermo has a quick comment. Sorry, let me unmute you very quickly. Yes, you should be able to speak now.
Great, thank you. So I like it. I like the results a lot. I have a quick comment because I think in both cases what you do is very, very similar. I mean, of course, you said it's very similar, the number field case and Z to the N. So I think you could do it in general. What do I mean by that? So you define a ring, an N ring, so an N-dimensional free module over Z that has a ring operation. And what you do in the first case is count index subrings, and in the second case, you're counting discriminant, which you could say, but why do you do the discriminant? But it's sort of the same thing because it's sort of the discriminant of Z to the N. You could think somehow like it's one, and actually counting by the discriminant, what would do is taking the index square. I think that's why you get the square root of the B in your second case with the number of fields. And the fact that you get the automorphism group of the ring is sort of in a sense, the automorphism group of Z to the N as a ring is just it's like N factorial or something. You just sort of trivial, or N factorial minus one. So you could do it in general. I don't know, just it might be worth do a more general case, and both cases are a particular case of the same thing. But I'm that's just my comment.
Yeah, no, that's a good comment. So there's a couple ways to find these lower bounds for subrings. So when I stated, or this way, I guess I'll say, we're not sure kind of if you give kind of a more general ring, what the multiplicative structure looks like. So we're unsure if it makes sense to kind of study multiplicative closure in this way for those problems. But if we quickly go back to Brackenhoff's bound here, this actually holds for any subring in the ring of integers of any number field. So we can, we've also studied looking at expanding this bound. The problem is the bound you get is a little more complicated, so it's harder to study the series you get in the end.
Great.
All right, cool. Let's thank Kelly again for a really fun talk. I think we're supposed to start at